Okay, so maybe I know this is not fashionable, a couple of words about ethics. So what I'm showing today, it did not use inordinate amount of energy and water compared to the expected outcome. It's not relying on stolen intellectual work, and I'm not encouraging my students to stop learning or flood the publication systems or flood MathLib or any open source effort or stop improving Lean by writing better automation. So in short, yeah, no generative AI was used at all for this work. So what is this work about? So it's about teaching using Lean, but when you want to teach using Lean, there is a very important question, which is, what is the end goal? Do you want to teach Lean, or do you want to teach logic, or do you want to teach mathematics? And all those goals are great goals, and it's of course very interesting to learn about Lean, and it's interesting to learn about logic, and it's interesting to learn about mathematics. But what I'm talking about is all about teaching mathematics using Lean, not teaching Lean or not teaching logic or type theory or anything like this. So there are community resources if you want to use Lean for teaching. There is a web page with links to existing courses and tricks that you can use on existing libraries. So check it out if you don't know about this web page. And so the general context, again, is using interactive theorem provers to teach mathematics reasoning to first-year students, so very young students. And the goal is to improve reading and writing of proofs on paper. So there is no technological goal, no Lean expertise, no type theory goal. And for instance, this is what Heather Macbeth was doing at Fordham. But no, she's at Imperial doing other things. But I'm not, of course, I'm not the only one. And I should have added that Siddhartha Gadgil is now also using Lean with similar goal and what I'm going to show in Bangalore. So the specific teaching goals are the following. So first, I want my first-year student to have a really, really clear picture of the proof state. So the proof state, of course, is very familiar to people who use Lean, but on paper, it's not a concept that is visible at all. So I like the Alex Kontorovich has a nice comparison about that. He says the way we teach mathematics is similar to teaching chess playing without using a chessboard, just by describing the moves, in algebraic notation. I don't know, pawn goes to d4, and you never show a chessboard to students. And of course, very good chess player can play chess in their head without a chessboard, and in the same way, a mathematician can do mathematics without looking at the proof state. But I want students to learn how to build a proof state in their head, and it's easier if at the beginning Lean shows the proof state. And I want students to really distinguish what is stated, what is proven, what is used, and it seems obvious, but if you attend a talk by professional mathematicians, they would use the same word. I mean, and I include myself in this. I'm not saying everybody is doing it wrong and I'm doing it right, but when we talk casually, we don't really distinguish claiming there exists an object such that whatever and fixing this object. And sometimes we don't distinguish between stating P implies Q and using P implies Q, or stating for all X something and starting a proof of for all X something. So this it's much easier with a proof assistant to be rigorous about this and really consistent. And then when everything is clear like this, you can have students reacting to the goal shape, to the syntax of the goal, and so that they can alternate between times where they simply react to the shape of the goal, to the root of the expression that they have to prove, and times where they need to think and decide something. And this is related to the last point I listed: identify risky or irreversible steps compared to just routine reversible steps. And it's much easier to do with a proof assistant, and it's much easier to see what is bound and what is free, because when you introduce a variable in Lean or in any proof assistant displaying the tactic state, you can see that a variable is a free variable that can interact with the other lines of the tactic state and interact with the goal, and which variables are bound by quantifiers, by lambda abstractions, and so on. So this is what I want to work on with my students, and there are challenges. In the beginning, when I was teaching using, I spent 2 years using the model, and of course, Lean syntax is for experts. Lean use, and students liked it. They were able to prove stuff with Lean, but there were 2 issues. So sometimes Lean was too smart or not smart enough. So too smart means Lean was doing the whole exercise. For instance, I had to be careful with linear the linear arithmetic tactic, doing too much work, or of course, I did not teach students about the simplifier or things like that. They could just crush the exercise. But sometimes also the Lean was not smart enough, meaning it was asking for details that I would not ask on paper. And when I say smart enough, is again, it's not an absolute statement. It's in this context where I want to improve proofs on paper. When Lean asks for a proof that I would not ask for, and nobody teaching first year undergrad would ask for on paper, then I say it's not smart enough. It doesn't mean that it cannot be smart enough. I mean, it's that it should do more in other contexts. But in this context, sometimes it's not good enough. And more importantly, the skill transfer to paper was disappointing. So it means students could solve the exercise in Lean, and then when I told them, no, write a proof on paper, even after doing this proof with Lean, it was disappointing. The writing was not good, some steps were missing, or they would copy the Lean syntax too closely, and that would be unreadable for someone who is not a Lean user. So the Verbose Lean library, it has really 2 components: a control natural language input as a new front end, and dedicated teaching tactics as backend. And very often I fail to communicate the fact that those are really 2 equally important, or you could even say the control natural language input is only the tip of the iceberg, because without the dedicated teaching tactic as backend, it would not allow me to reach my goals. And I will show you what it looks like. And of course, I'm now using Lean 4, which makes all this a lot more flexible and possible. And there is another library, the Rock Waterproof library for the Rock Proof Assistant, that shares very similar goals. And we started roughly at the same time, and then shared a lot of ideas, and now both of those libraries got better as a result, and now the Rock Waterproof people mostly switch to Lean anyway, and so I will tell you later what this will bring us. So the 2 important things, so the goal is not to make input easier. I mean, the students were able to prove lemmas in Lean already from year 1, when I was using a completely vanilla Lean 3 and Mathlib. The goal is to improve skill transfer to paper proofs, and the automation is also very important. So let's see a non-example. So I think it's interesting to compare what I mean by not achieving those goals. So at this URL, you've got Alex Kontorovich real analysis game, which is teaching elementary real analysis, but without a dedicated teaching library. And let's see what it looks like. So if we go to 2 files from that library, I don't know if this is this big enough, or should I write this bigger? Maybe a bit bigger. So those are 2 files from the real analysis repository. So it's not only code repository. It's also a Lean4 game. So just if you know about the natural number game, you can play this real analysis game as well. And so here are two examples of exercises. So the first example on the left is saying 1 over n goes to 0 when n goes to infinity. And so it's clear we want first-year students to know how to prove this. And so the Lean script on the right is using change, intro, lots of have, the choose tactic, the specialized tactic, lots of have, bound, linear if, exact modcast, which is handling the going from the natural number capital N is less than the natural number lowercase n to the same thing for real numbers. And this, for instance, in particular, I mean, it's really emphasizing the difference between natural number and real numbers, the fact that the inclusion of natural numbers into real numbers is not really an inclusion, there is a coercion, and you need to transform the inequality between natural numbers to inequalities between real numbers, and then learn a lot of lemma names. So in that case, not too many, but in the other proof, we'll see more. Okay, and then this proof is really hard to transfer to paper. After writing such a proof, and this is what I did in the beginning too, I mean, students are basically at exactly the same point in terms of writing ability on paper. And now the second example is, I mean, again, lots of halves, lots on rewrites, and this is proving that n goes to -1 to the n does not converge. So this sequence, n goes to -1 to the n, is not a convergent sequence. And you can see a lot of work done on those computation, applying apps add, applying apps neg, and all those lemmas that don't have names and on paper. So now what does it look like if we do those proofs in Verbose Lean? So now I'm switching to Verbose Lean. And maybe I will, if I open this file. So the first one we were looking at is 1 goes to 1 over n converges to 0. This is what it looks like. So exercise, n goes to 1 over n converges to 0, and there is no data and no assumption. The conclusion is just a sequence, n goes to 1 over n converges to 0. And the proof looks like a kind of a rigid mathematical English. So we fix epsilon, which is positive. We obtain n such that n is bigger than 1 over epsilon. So this is using the Archimedean property, which was used, of course, also in the other proof, but was called by name. And then let's prove that n works, and we get the computation is, there is one line of computation to get that capital N is positive, and then 3 lines of computation explaining. So by computation means there is no assumption used here, this by computation, and the other 2 lines, there are assumptions that are used, and so they are mentioned. And there is no coercions of natural numbers into real numbers or casts or anything that is mentioned. And for the n goes to -1 to the n does not converge, it's again, so it's a more sophisticated, maybe I will remove the tactic state proof, but it's you don't have all those halves, you have a forward reasoning without lemma names. And so I say, take a look at this line that is here. I say, since for all n bigger than capital N, absolute value minus n to the n minus l is less than 1/2, and 2n is bigger than n, we get that. And you can see that the Lean is not asking for a proof that 2n is bigger than n, and the automation is set up so that this does not require a justification, because you would not ask for a justification on paper. You need to mention that fact. I mean, if you remove that fact, then you will get an error, could not prove. So let's see the error message. So I could not prove using the given fact So that n is a real number, capital N is a natural number, and the only given fact is the one that was mentioned, and I could not prove this goal. So there is you need to mention everything, but not provide proof that you would not provide on paper. And so that's what it looks like on those kind of examples. Let's see maybe more interesting examples where we can see automation working a bit more. So so this is so there are different styles. Maybe I can show very quickly this aspect of supporting different proof styles. So remember, if I want to prove that continuous functions are sequentially continuous, I mean, you can give a proof term. So you can just fully prove this by providing a proof term without using any tactic. So this is using the eliminator of existential and basically nothing else, and the rules of lambda calculus. And then the second example is a proof, the very same proof done using normal Lean tactics. And then the first layer of control natural language that you can choose to use is the just very thin layer of control natural language. Like instead of, you see, instead of this line, R cases, HF, epsilon, epsilon post with delta, delta post, H delta, you can write something like by HF applied to epsilon in epsilon post, we get delta, delta post, and I don't know what this one is called, HF and not that, but that would be the first layer you can use. It's already to transfer to paper. Skip to fully automated and as close as possible to the paper proof. So here I just write, since f is continuous at x0 instead of saying by hf, and I mention that epsilon is positive, and I get a positive delta, and so on. So this is how I do the R cases in that case. And this line would be the let proof that n work, would be the use capital N from the tactic proof. And here I do a bit of backward reasoning with it suffices to prove, and so on. So this is already way easier to transfer to paper, but it's not doing so much automatic work. And so let's see an example where something more is happening with the automation. So here I'm proving the squeeze theorem. So I've got two sequences of real numbers converging to the same limit L, and I assume a third sequence is squeezed between U and W, so V is squeezed between U and W, and the conclusion is V converges to L as well. And here, so in the beginning, it looks like I'm only doing intro, or that first line would be only a change, second line would be an intro, I mean two intros and two R cases. But then here, when I say fix n bigger than max and n prime, the assumption that is introduced on the right is just automatically named NGE, is that n is bigger than max and n prime. But then on the next line, I carelessly say n is bigger than capital N, and the computer is happy. It's not asking why n is bigger than capital N, because the automation is set up by the teacher so that the lemma saying that if A is bigger than max and of B and C, then A is bigger than B, is an anonymous automatic lemma. So it has no name, and it's automatically applied, and I get some conclusion. And then when I want to prove that absolute value of Vn minus L is less than epsilon, again, I used a lemma that is registered and is mentioned in the lecture before, that this is equivalent to proving that minus epsilon is less than Vn minus L and Vn minus L is less than epsilon. And so I just announced I will first prove that, and then Lean creates a second goal for the other inequality. it's okay applying this lemma. And in the computation, again, this lemma, but in the other direction, is applied, because this is an if and only if. This is applied in the other direction automatically. I say minus epsilon is less than un minus L, since absolute value un minus L is less than epsilon. And here, Lean is okay with this justification. And then going from un minus L to Vn minus L, I just say since un is less than Vn, and this is accepted by as a justification. So what is happening here? If I ask Verbose Lean to comment on what it's doing, so that set option trace.verbose true is not an option that students use. It's for teachers preparing their lectures. And here we can see what happens. For instance, here is the first tactic where something interesting happening. So the trace is telling me Verbose will try to derive the two facts that were announced by since, so the for all and the fact that n is bigger than capital N. So let's see how this was done. So, I mean, the first one is not very interesting. It tried all the assumptions. So it says we'll not try to apply each local assumption. And where is it? Okay. Where the message is repeated. But so it tried applying U, that does not work, and so on. And HN is exactly this assumption, this claim I was making. So that was not very exciting. But if you look at the other, what was it? Yeah, so the other thing to prove, n is bigger than capital N, did not follow from a local assumption, did not follow from linear if only, and it followed from anonymous fact splitting lemma. So this is where the system is trying to apply lemma that were registered by the teacher. And the lemma that succeeded was LE of max LE left. And so that's how you see what the tactic was doing. And after deriving those facts, it proved the goal using only those facts, and that worked easily. And yeah, we can also see the similar things, what the calculation did, and so on. Okay, so the last thing I wanted to show was how you can get help when you're a student doing this. So here, there are two levels of help. First, you can type help when you simply don't know what to do at all. So, of course, teachers can disable this tactic if they are really tough teachers. But the goal of the help tactic is that remembering the syntax is not an issue. So if you know you need to introduce epsilon, but you don't remember how you do that, then you can type this help tactic, and the help tactic comments on what the goal looks like. So here it has 3 comments and 3 suggestions to make. So it says the goal starts with the application of the definition, so you can make it explicit. So it proposes to unfold the definition, and again, this is completely parameterizable by the teacher. You need to opt in this definition unfolding, because of course you don't want the help tactic to suggest unfolding the definition of real numbers or addition of real numbers or things like that. So the definition of converges to was marked as something that can be unfolded by help. It says also you can start a proof by contradiction. This is not very useful here. Or it says the goal starts with for all positive epsilon, hence a direct proof starts with fix a positive epsilon. And as usual, you can accept this suggestion, and then of course the rest of the proof becomes invalid. So you can do that, and you can do that also with assumptions. So if I know I want to use HF, but I don't know how. You can ask about help about HF, and this is the reason why the assumption names are mentioned in the tactic state, although they are not mentioned anywhere in the tactic script. And so we have this. This assumption starts with an application of a definition. So again, you can unfold, or you can yeah, it gives you the syntax for since f is continuous at x0, and very importantly, it does not tell you what you should specialize the assumption to. I mean, the students still need to find a relevant positive real number. So the help tactic tells the student that they need to choose epsilon 0, a real number, and the positivity of epsilon 0 must follow immediately from an assumption. And then the name delta can be chosen among available names. And the system will complain if the name is not available. We don't want students to do shadowing of names because they would do it unwillingly and then become very confused. And again, it's great that Lean does shadowing for expert users, but for first-year students trying to do mathematics, it's very confusing. So that's the first level of help, and there is also a help widget. So you can also simply select stuff in the info view. So if I select the goal in the info view, I get suggestions, and so I can accept those suggestions, and then select assumptions, like I select HF, and then I select epsilon, and then the what is, oh, it's confused because there is an error message with the end of the proof. Otherwise, if Lean is happy that there is no error message, you get suggestions. So, and the suggestions, again, are parameterizable by teachers. But here, when I suggest a statement that starts with a for all real numbers and then a real number, by the default configuration is to suggest applying the continuity assumption to epsilon or epsilon over 2 or epsilon plus 1. So here you get to choose, and sometimes epsilon over 2 is a better choice, but here epsilon itself is good, so you can accept this suggestion and so on. And so in that case, we could do the whole proof simply by clicking on. By the way, I'm using NeoVim. So I'm not clicking around. I'm just using my keyboard. But of course, this works in VS Code, and in VS Code you can just click around and without. Basically, in VS Code I could do this as a keyboard at all, just by clicking in the. So that's the second level of automation, and it's all configured by the teacher. We can see what it looks like to configure this by going to the library. I have got an error message. So, I mean, in my library, of course, I've got definitions and notations. So this is just pure ordinary Lean code and a bunch of lemmas. But then I configure the anonymous, so-called fact splitting lemmas, and here you can see somewhere the lemma that was applied automatically earlier, the fact that if max AB is less than C, then A is less than C. So that was a lemma applied automatically earlier in my demo, and it's applied automatically because it's mentioned here. And the same with different kinds of anonymous lemmas. And the data providers that we use with the widgets and the suggestion providers are also configurable, but here I'm simply telling Lean to use the default ones. And the help providers are configured by the teacher. And this is the list of unfoldable definitions, again, configured by the teacher. So depending on what you're teaching and how much assistance you want to provide, it's all customized here. Okay, so I think I will go back to my slides. I forgot to say, Verbose Lean, of course, I'm using it in French because I'm teaching French undergrad students, so there is no way I can teach in English and or use the English sentences as Lean proofs. So the Verbose Lean as an internationalization framework for tactics and messages and error messages. So English, at least my version of English, is supported, and and the French is supported, and there is a Spanish version that is PR'd to the repository, and I need to find someone who can understand Spanish to check the Spanish version is okay, and people in the Netherlands are planning a Dutch version, and you can add your version. And yeah, the demo, I already looked at it. So I want to insist a bit on the since tactic, which is kind of the main tactic of the framework. And it's really important to understand it has two completely independent stages. So when you write since A and B, we obtain C. So for instance, I did that. So when was it? Yeah, everywhere basically, but yeah, since f is continuous at x0 and epsilon is positive, so of course there could be only one claim or more than two claims, but so I've got say 1, 2, 3 claims. A, B are claims, and the first step is to stop here and independently try to prove A and B from at most one local assumption and the registered anonymous lemmas. So, and they are done really independently, and they must basically follow from at most one assumption using one step, one lemma, one little computation that you would not justify on paper. And sometimes the students complain that it's not doing enough, but it's not doing enough on purpose, because I've decided to have automation asking them to do one step at a time, but without asking for details I would not want on paper. For instance, this proof that we've seen of sequential continuity of continuous function, a general automation tool like the canonical tactic by Chase Norman and his collaborators, it does the proof entirely. And the automation in today's Lean can just completely crush the exercise, but that would be teaching nothing at all. So independently try to prove A and B, no fancy things, and then in step 2, try to prove the claim. We obtain that C, try to prove C using only A and B and the registered lemmas, and not doing several steps, doing one thing only. So when using this library, you need to be really careful with those registered anonymous lemmas, because they are lemmas so that would not have a name on paper and would not be mentioned at all. And you need to think of all the ways students can try to do something that is reasonable in your exercise, and not only the path that you have in mind. So sometimes it involves I mean, kind of a smart work. I mean, you need to think, yeah, how could they approach this problem? But sometimes it's completely stupid. And the examples I'm showing here is an example of a completely stupid obstacle that you will face if you're not careful and when using Verbose Lean or any kind of interactive theorem prover for math teaching. So say you have integers a, b, c. When you say there exists c such that b equals ac implies a divides b, and this is true. And the fact that if there exists c such that b is c times a, then a divides b is of course also true. And I say this for people doing computer science and software engineering. I mean, for most mathematicians, it's really, really hard to see the difference between those two lines. And one of those two lines is the definition of A divides B in MathLib, and I don't know which one is the definition. So I don't know, but I know that I registered the other one as an anonymous lemma. So if the goal of the exercise is to prove A divides B, and the students say it's enough to prove there exists C so that B equals C times A, or if they say because B equals 2 times A divides B, it works. And if they say because B equals A times 2, we conclude that A divides B, it also works. And students don't want to know, and teachers don't want to know which one is the definition. and which one is a lemma using commutativity of multiplication. So that one is really silly, but it actually happened to me. I mean, I had to tell students, "Oh, I'm sorry, you've not been careful when reading the definition." Of course, I was recalling the definition of A divides B. I mean, the one that is in MathLib, not the other one. But still, I mean, I mean, when you claim you want to prove rigorous, you want to teach rigorous proofs in mathematics, and it's an important topic. If you're stuck on something like this, it really ruins the credibility of saying this is it's important to be rigorous. Because if you say, it's really important, if you're discussing divisibility of integers or natural numbers, to remember if the definition has A on the left-hand side or on the right-hand side, I mean, it's really not reasonable. And then students just remember that this course was about being extremely pedantic and not about mathematics. Okay, so there are still challenges. There is still a slight cognitive dissonance introduced by controlled natural language. So what I mean by this is, when you look at the code, it looks free-form, but it's not at all free-form. I mean, if you miss one letter from one of those words, there is a syntax error. But so sometimes at the very beginning, students want to just write sentences in whatever free form, but it's very rare, and they understand very quickly. And when there is a syntax error which is due to a typo in a word, then it's very easy to see. And the syntax highlighting immediately stop highlighting the word because it's not recognized. And there is the error message says unexpected token, and then the word is mentioned. So that's very easy to fix. It's harder to understand the error message if you have indentation issues. I mean, when Lean says expected call GT as an error message, I mean, this is of course harder for students, but still it's less hard than I feared at the beginning. A kind of a deeper challenge is this story of balancing the expressivity of tactics and the requirements on student memory. So what does it mean, expressivity of tactics? Once you start writing those controlled natural language proofs, it's very, very tempting to want those proofs to be as nice as possible and as close to paper as possible. And then, if you want to reach that state, you need to introduce variations, and many variations on the tactics, doing slightly different things so that you can have really efficient sentences. And you need to resist that temptation, because every new variation puts a burden on memory requirement, and students may start mixing up the variations, and then it gets out of control. And of course, the expected automation level is never fully specified. And so when I say I want Lean to do all the proofs that I would not want to see on paper, and I want Lean to not do the proof I want to see on paper, I mean, this is extremely vague specification, and sometimes there is a mismatch, and still the automation level is not exactly right, and the students still have work to do to go from Lean to paper. And in very rare, there are difficulties with foundations. I mentioned of this number to mentioning the coercion of natural numbers into real numbers when discussing the sequence 1 goes to 1 over n, but sometimes in very specific situation, you cannot avoid it completely, but it's very rare. It's really very rare, and I spend zero time discussing foundations with students. At the very beginning, I did. I mean, I wasted time explaining, usual mathematics is based on type theory. We use type on the set theory, and we use type theory. It's slightly different, but this was completely beyond them anyway, and completely useless. And I mean, they don't even see the difference between writing X, comma, real number and X belongs to real number with the membership notation. It's completely transparent to them. So future work. Currently, we have a grant, an education science grant, which is called the APAM project, led by Cécile Ouvrier-Buffet, a colleague in mathematics and education science for mathematics, and Cécile and her PhD student Clara Cisco, they came to my lectures several times during the semester. So I'm currently teaching this, and they look at the students, they record stuff, and by the way, if you're interested in, I should have put a slide on this, sorry about that. If you're interested in recording what your students do in VS Code and then doing something with this recording, you should know that about 6 months ago, Mark Wiesinger from the FRO revamped the logging infrastructure of the VS Code extension. So now you can very precisely say which LSP communication between VS Code and Lean you want to log into your log file. I mean, when you switch on log, I also have a tiny VS Code extension just displaying a record button, and the students can click on the record button instead of going to the VS Code settings and look for the VS Code logging setting. So they can click on record and then click on stop, and it will start writing the log file and stop writing the log file. And then Antoine Meyer and Pierre Boutry, they made a Lean program. I'm using Lean as a programming language to read the log file and reconstruct the various static states and the error message. So all this information is in the log file, of course, but it's hard to read JSON file. And so they have a program that is still work in progress, but already doing this work, of course, relying a lot on code that is already in the Lean code base. I mean, that's one of the fantastic things of having the Lean LSP server written in Lean itself. I mean, if you want to work on the LSP log, you can do this using a Lean program and having access to all the Lean functions that are actually used by the LSP server of Lean. So that's really nice. Okay, so we are recording all this. They are talking to students, and especially 4 students who are who volunteer to be studied by those education science people, and so hopefully in maybe 6 months or maybe a bit more, I will have more to report, or they will have more to report. And then the future work, automation tweaking is endless because, of course, it can always be better, and it requires, every time you try a different style of exercise, you realize, maybe automation should do a bit more here and a bit less here. So there is some tweaking going on. It's much more stable than 1 year ago. I mean, 1 year ago, I was tweaking automation every week. When I was 1 year ago, I used Verbose Lean with Lean 4 for the first time, and so I was tweaking automation with every new exercise, basically. But no, it's pretty stable, but still evolving, and the waterproof team. So Yim Portuguese is the main person developing waterproof for since 2019, I think, or maybe 18. And Pim Otter is a PhD student in Utrecht, also helping a lot. And they are working on, helping me with Verbose Lean, and also working on the more user-friendly VS Code extension. So this is something they had for their ROC library, and it's very nice because instead of having the mathematical explanations and comments and hints as comments in the Lean code. It is displayed as nicely rendered markdown, including mathematics, and the students can type only in dedicated zones where they need to type the solution of the exercise. They cannot ruin everything. Maybe I don't know if you have noticed, but in the in Verbose Lean there is a QED at the end of the proof. And this QED is, so it's displaying the victory widget, which is more impressive in VS Code because it's bigger. And it's helping making sure the syntax error do not leak to the next exercise. But sometimes students just delete the QED error message and then the QED token, and then they get an error message until spanning all the range until the next exercise, and they're confused about this. So this will all disappear with the waterproof interface, and the help will be nicer to navigate to. So that would be nice. And I forgot on the library side, the counterexample generation would be nice to integrate. So instead of saying what you said does not seem to follow from the fact you've stated, so which would be the message, the error message you could get. I mean, we could try to say, here is a counterexample with what you know, what you claim cannot be proven, or something like this. Something maybe built on top of plausible or something. And it would be nice to also leverage the wonderful work that David Sren Christiansen did on Verso at the Lean FRO2. So there is an example by Heather Macbeth that I can show. If you look at the this file by Heather, you can see there are nice explanations. So this is a nicely rendered web file by Verso with some dialect of Verbose Lean used here, because again there are many different styles that are supported, and you've got the tactic state display of Verso and a nice syntax enlightening on your website, and this is of course also very interesting use of Verbose Lean and Verso. And I will stop here and take questions if there are questions.
Thank you so much.
Or maybe I'm alone and nobody is listening. That's the joy of remote talks.
In what they do as well.
What?
Right-hand side. The right side.
Okay.
Yeah.
Okay. Hi. Okay. Thank you so much, Patrick. Now I've realized that Teams Live does not record our applause because I saw this on YouTube. So instead of applauding, we'll have to whoop. Can everyone in the room whoop? Woo! Thank you.
Thanks.
Thank you. That was a lovely talk. So we've got one question already in the Q&A. So I know you started by saying that you didn't use lots of water and so forth, but here's a question about that might involve using water. Did you have an LLM like Claude formalize material using Verbose Lean?
No.
Oh, and you're not interested in doing that, or are you in?
Yeah, unfortunately, I don't have another planet, so I need to use the only one we have.
Okay.
And so I don't think it's worth doing such damage. So no, but I'm sure it could. I mean, so some people told me one of the nice points of using Verbose Lean is that the LLMs are not as good as Verbose Lean at writing Verbose Lean as they are at writing ordinary Lean code, because of course the available sample is much smaller. And by the way, my exercises, I forgot to put a link, but people who are interested in the exercises I'm using with my students can find them on my GitHub. So the repository is called Proofs with Lean or something. And there is also a Verbose Lean demo repository, so you can find all this code online. And the solutions to the exercises are not on the public GitHub, but of course, if there are teachers who want solutions to those exercises, I can send those solutions. But so yeah, the training data is extremely scarce, but every exercise file includes examples, of course, for every new tactic or every new logical operator or quantifier. Of course, I write examples before students need to do anything, and I suspect that good LLMs could just use those examples and solve all the exercises. Yeah, but sure.
Oh, yeah. So there's another question about Heather Macbeth using Verbose Lean. The question is it an indication that she's moving towards using Verbose Lean for teaching?
I think she experimented with that. So the thing is, so of course, Heather is very well known for her book, the Mechanics of Proof, and the teaching tactics. And by the way, some of her teaching tactics are also reused in Verbose Lean. I mean, Verbose Lean is using every tactic it can find, and so I'm thinking here about the variants of G-Conger that were originally at least partly teaching tactic, although they are very useful also for serious use, I mean for professional use of Lean. But the thing is, she moved from Fordham University to Imperial College in London, and the students she has there are not the same students and not taking the same classes. So I think she's no longer teaching using the mechanics of proof, but not because she no longer believes in this style. It's simply because she's no longer on the right side of the Atlantic to use that. And I think she just wanted to experiment with Verso and experiment with Verbose Lean, and you would ask you would have to ask her if you want more detail. And I should say also, when I'm on the topic of Heather, the fact that all the exercises you've seen do not use any lemma name come also partly from a conversation with Heather, who is very insisting a lot on the fact that we don't want students to see names of lemmas like Adley, Adeli, or whatever. And I mean, I was already on that path, but that was reinforced, and also reinforced by talking to the waterproof people. I mean, it's all really a collaborative effort. I mean, you should not think, and this is only Patrick suddenly deciding what needs to be done for undergrad teaching using Lean. That's really, even if I'm the code of Verbose Lean is almost entirely mine. I mean, with crucial help from Kyle Miller and Mario Carnero for the most tricky metaprogramming bits, but it doesn't mean it's not influenced by many other great people.
Well, thanks. So here's a question. Perhaps you've already answered it by talking about what the instructor can write. But the question is, can there be a setting of what is trivial, say? You said that you don't want to see a proof of 2n is greater than or equal to n, but I can claim I don't want to see a proof of the convergence of 1 over n in a proof.
So you need to, I mean, in the case of 2n bigger than n, I think that one is currently not customizable in the sense that it's just linear if only with no lemma, no fact will prove that. And I mean, I could add an option. I mean, if you're sad about this being considered obvious, I mean, it would be very easy to add one more switch that teacher could choose to enable or disable. What is currently fully under control is really the lemmas that are applied in the process, but indeed, when I call linear if only, it just calls linear if only with the full power of linear if only, but which is much weaker than calling linear if and saying nothing else, because linear if will look at all the current assumptions and do all kinds of linear combination of assumptions, and this I definitely don't want to be done automatically. Yeah.
Is there any way in which the proof informalization work you've done with Kyle Miller could be used in conjunction with Verbose Lean, for example, to summarize developments and make them more accessible to students?
So Yeah, sorry, I wanted to add one more thing about the. You said maybe you want the fact that 1/n goes to 0 to be obvious. I mean, you
Yeah.
can definitely later in the course you can add this to the database of obvious lemmas, and then when you do the I mean, no, in a week 2 or 3, you prove 1/n goes to 0, and they have to prove it. But then 2 weeks later, it's in the database of the next. Exercise. You can even, instead of having an exercise, you can have an exercise lemma, and whose conclusion is immediately added to the database after the exercise lemma. And of course, you can build. This is not a static thing. You don't have to decide on day one of the term what is obvious and what is not. It can evolve. Okay. So sorry. So that was a complement to my previous answer. So. Okay, verbose lean and informal lean, they move kind of in opposite directions. So the verbose lean is an input language and a tactic framework, I mean tactic library, and the informal lean is turning usual lean tactics into informal text. So they are kind of going in opposite directions, but in principle there is nothing preventing you from combining both. But if you, I don't know, the text written in verbose lean is meant to be already readable. So I don't really know what informal lean would do. It would not be much better, because I mean informal lean is also a deterministic program. So it won't write flowery sentences and poetic explanations about what's going on. I mean, so it is also a bit robotic at times, and so it's meant to be understandable without any training in lean, but it's not meant to be poetry.
Okay, I've got a question myself then. How easy is it for people to transfer from using verbose lean to using non-verbose lean?
It's hard. I mean, it's really again, it's totally a non-goal of the whole project. It's not. I mean, it's not completely independent, because understanding the concept of the tactic state and the current goal, I mean, this is completely common between ordinary lean and verbose lean. But then everything else feels different. So sure, it's a lot of work. I mean, there is no common tactic name. I mean, you can learn that the easiest tactics, the ones that are not interesting, have direct translations. Like if you say fix X, you can teach in 10 seconds students that this translates to intro X in ordinary lean, but that won't help at all with the core of the proof using the since tactic, and that is applying lemmas automatically and doing a very limited kind of reasoning. And so yeah, it's simply a different story. And of course, teaching how to use lean is also a very interesting topic, but it's simply not the goal here. And yeah, but there have been people. I mean, I have students who took this course in their first year, and then 2 years later they come back to me and say, I want to do a kind of an internship with you writing ordinary lean code. I mean, I have some currently who took the Verbose Lean course 2 years ago, and I know they want to write ordinary lean code, but this is pretty rare. And
yeah, and as you say, not a goal. The other thing that was interesting to me, as you mentioned, is the possible different routes that a student could take to write the proof, and then you have to try to imagine all the possible ways the student could write a proof.
So of course, that's not specific to verbose lean. In a sense, if you teach using ordinary lean, I mean, you need to decide what are the lemmas that you give to students, and if you do not decide, if you just tell students just search mathlib or use apply question mark, then you risk completely skipping the exercise. I mean, if apply question mark says, yeah, sure, here is a proof that is already in mathlib, then you lose. And so that's not specific. The fact that different proofs require different lemmas. It's not specific to Verbose Lean. What is specific to Verbose Lean is that the lemma names are hidden. And of course, I state the lemmas for students. And the students, they see sentences like the database of lemmas from this course know that this fact is true and this fact is true, and they don't have names, but they are stated, they are given explicitly. Otherwise, I mean, guessing what are the lemmas that are available would be extremely frustrating.
Yeah, thank you. And we have time for maybe one more question. Oh, okay. So we had one earlier question, which is, could we combine? So one question was, is Lean and Verbose Lean separate worlds, separate languages? Should they be merged into one super Lean?
Okay, I can answer that because I mean, yeah, it's a good question because it's too obvious to me because I'm so deeply immersed in Lean, but Lean, especially Lean 4, is a kind of fantastic language that is extremely flexible, and the Verbose Lean is built on top of Lean, and it's in Lean. I mean, it's not at all an independent program. And if I guess I'm still sharing my screen. If I write intro epsilon here, it just works because an intro epsilon post, and now I have one line of ordinary tactics in the middle of my Verbose Lean proof, and sometimes I do that while preparing the my exercises, and Lean does not complain at all. I mean, it's and the there, and I can call proof if I want to type, or can code. Those are not at all separate worlds. It's just the amazing flexibility of Lean 4 that empowers you to build all this purely from user space. Maybe with help from expert users, like I mean, in order to have incremental elaboration and stuff like this, I mean, I needed Sebastian Ulrich to tell me about how to make this my statements and proofs enjoy the benefits of incremental elaboration, for instance. But still, I mean, Sebastian did not modify the Lean core for that. He just told me how to use Lean's flexibility.
Oh, thank you. So okay, there is one more question. Maybe we'll come back to it in a panel session, and hopefully you'll be able to join using this this technique too. So the question maybe you'll think about for the panel session is talking about the logistics of how you teach with Verbose Lean. We'll come back to that later. But for now, let's all thank Patrick, using, not with clapping because that doesn't work. We'll have to whoop. So let's everyone whoop. Woo! Woo! Okay. Brilliant. Thank you so much, Patrick, and hopefully we'll see you again for the panel session.
Yeah, I'm sorry I was not able to attend yesterday on Wednesday, but today I want to attend talks, and hopefully Teams will let me attend talks. It did not let me give a talk.
Oh, yeah. The attending you can definitely do through the browser. It's the presenting that it won't let you do. So we have now a 5-minute break before our next talk. Thank you so much, everyone.